So in this video, we're going to get a lot of practice with the disk method of calculating 3D volumes. So we're going to take some areas and rotate them about the y-axis, the x-axis, and any vertical and any horizontal axis, just to give you a feel for any type of disk problem you'll be asked to solve. Alright, so let's start with this one. So we want to find the region bounded by these curves. So let's sketch these curves. Start out with this one. Now, this equation is in terms of y. And it always makes me a little uncomfortable when we have an equation in terms of y. So I can just get y by itself to get the same curve just in terms of x. So it's easier for me to graph. So I will divide 2 on both sides of that equation, and then I will square both sides so I can get that y by itself. So here's our same curve as this one. It's just in the form of x, in terms of x, but it's the same curve. And that's just a lot easier to visualize. This is just going to be some parabola, like that. Alright, got it. X equals 0 is the set of all points that have an x-coordinate of 0. So all of these guys. So that'll just form basically the y-axis. And y is equal to 9. That is all the points that have y-coordinates of 9. So just this horizontal line up here. Okay, and the region bounded by these 3 curves will be this one. And they want me to rotate this region about the y-axis. So just this same x is equal to 0 line. So if we take this area and sweep it across that y-axis, we'll get some 3D volume that looks like this. A tall bowl. Alright, so let's see if we can visualize this 3D shape as a bunch of disks stacked onto each other. So we can definitely do that, which means we can use the disk method to calculate the volume of this shape. There are other 3D shapes that you can envision as a bunch of disks, and you'd have to use other methods. Alright, so let's start with our disk procedure. Let's form the radius of these disks. Here's the radii of each disk. On our main graph, those are going to be these lengths here. And I notice that these lengths are simply the x-coordinate of each one of these points along that green curve. Now, because these are x-coordinates, I want an equation that gives me the x-coordinates of these points. That'll be this form of the green curve. I'll be using this equation rather than this one, because the one on top gives me the x's. And I need those x's because those are my disk radii. So 2 radical y. I put in a y, and I get the x of that point, which is the radius of the disk at that y. So moving on to step 2, because this is my radius of each one of my disks, I can square each one, times it by pi. So that will give me the area of each one of these disks. And now that I have the area of each disk, I need to multiply each one of these areas by a little bit of height. So I can get the volume of each one of these small disks. And this little height is dy. A little bit of distance in the y direction. So this will be dy. So this represents dv, the volume of one of those tiny disks. And of course I just want to add all them up to get my total volume. So for the bounds, what's my y lower bounds going to be? Well, it's going to be this right here. This is going to be my first disk I want to add at that lower y. And that y location is 0. And my last disk is going to be this one here. What is the y coordinate of this disk? Well, that's going to be y is equal to 9. So my upper bound, my y upper bound will be 9. And there we go, the integral is complete. And now we just have to do the math. So this integral is actually really easy. I'll just do that square first. That square gets me 4 times y, and I'll move that 4 and that pi outside the integral expression. So I'm just left with this. And that integral is just an inverse power rule. Just y squared over 2. And now I can put my bounds in. If I put 9 in there, 9 squared is 81 over 2 times 4 pi minus, gotta put 0 in there, but 0 squared is just 0. So my whole lower bound is 0. So this is basically my answer here. Let me just simplify that real quick. 4 divided by 2 is 2. 2 times 81 is going to be 162. So 162 times pi is my final answer for this one. Alright, let's do another one. Alright, let's do this one and I'll go through it a bit faster. Let's sketch this curve. That'll basically look something like this. X is equal to 1. All the points that have x coordinates of 1 and x equals 2 will be all these points. And of course, y is equal to 0 will be all the points that have y coordinates of 0. So basically just the x-axis. Alright, so here's our enclosed region. And we want to rotate it about the x-axis. So this axis right here. And it's going to be a small volume. We take this area and rotate it about the x-axis, we'll end up with something like this. Something like that. So we can imagine this shape as a bunch of disks stacked up on each other. Here are their radii. On our main graph, here are their radii. These radii are the y-coordinates of these points. So I need an equation which gives me the y-coordinates of these points. Boom, that guy. So 1 over x, plug in an x, and I get a radius of a disk. I want to square each one, times it by pi. That'll give me the area of one of these disks. And now I just need to multiply each one of these areas by a little bit of height. And this little bit of height will be dx, a little bit of x distance, to make that small disk volume. And of course, now that I have an equation, which I plug in an x and I get the small volume, that small disk volume, I just want to add up all of these small disk volumes. Now for the bounds. What's going to be my starting bounds, my lower x? Well, that's going to be right here. This is where my first disk is going to be. So what is the x of that disk? Well, it's going to be at x equal to 1. So 1. Now I'm going to add until this last disk right here at x equal to 2. So that will be my upper bound. And there we go. Integral is complete. I just have to solve it now. So we punch out this math, perform the square. I'll get 1 over x squared, the integral of. I'll move pi outside the integral. Now I know that 1 over x squared is just x raised to the negative 2. So I'll write it like that. And then I see that it's an easy inverse power rule. x to the minus 1 times negative 1. Alright. Let me throw in 2 in there. I'll get negative 1/2 minus, let me throw in 1 in there, I get negative 1. Can't forget that it's all multiplied by pi. And if I carry out that math in here, negative 1 minus minus 1, so negative 1/2 minus minus 1, so negative 1/2 plus 1, just a 1/2, times pi will get me pi over 2. Alright. Hopefully that wasn't too bad for y'all. Next one. Alright, let's do this one. Let's sketch this curve first. It's not too bad. It's just a line with a slope of 2 and a y-intercept of 0. Y is equal to 0. All the points that have y's of 0. And x is equal to 2. All the points that have x coordinates of 2. Going to be this vertical line. So therefore, our region bounded by these curves is this triangle. And we want to rotate this area about the x is equal to 2 line, which is just this one. Visualizing what 3D shape this area will make isn't too bad. Just going to be an upside down cone. Something like that. And this is disk method, so we want to see if we can visualize this shape as a bunch of those disks. And we can do that. So let's start executing our disk approach. Often the hardest part is bringing that math together to give us the radii of those disks. So, my picture up here, got a radii, got a radii, got a radii. Okay, now on my main graph, that's going to be these lengths right here. Now, the first thing I see is that, hang on a minute, these red lines are neither the x nor the y coordinates of the points along that green line. I mean, for this white point right here, this is the x coordinate and this is the y coordinate. So be very careful here. So it's definitely not going to be just 2x squared times by pi right off the bat. Definitely not. Let's take a look at our y is equal to 2x equation. That equation is giving me the y coordinate, these blue lines, of each one of those points. That's not what we want. We want those red lines. Those red lines are horizontal distances. So the first step in the right direction is getting x by itself for this equation, so that we have an equation that gives us the x coordinate of points on that green curve. At least that's a step in the right direction. That might not give us our radius, but at least it's a step in the right direction. So let's see. Alright, so I have x by itself. So now my equation allows me to plug in a y for one of the points and get an x. Plug in the y of this point, and that equation gets me x, and so on and so forth. Well, it gets me those blue lines. I need the red lines, so I'm still not done yet. So, this is one of those problems where it's really hard to find the radius. I'm going to have to use some sort of subtraction approach, maybe. So what I want to do is I want to take 2, remember here's our x is equal to 2 line, and I want to subtract off of it the x coordinate that the equation is giving us. Here's 2, and subtract off of it the x coordinate, that blue line. See how that subtraction is going to give us these little in-between red lines that we need. So I'm going to do 2 minus y minus 2 right here. One more time. Here's 2 to that red line, and I'm going to subtract the little x distance that this equation is giving me. And as a result, I get this remaining length. We're getting our radius. So I got the equation that gives me the radius, so of course I want to square it, times it by pi. And by doing so, we get the area of that disk at that y that we plug in. And of course, for this area, I want to multiply it by a little bit of height to make the volume of the disk. And this little bit of height is going to be a distance, a tiny distance in the y direction, so dy. So I multiply the equation that gives me the area by dy. So now it gives me the volume of one of those tiny disks. And of course, I want to add up all of these tiny disk volumes. This is a dy antiderivative. So I need a y lower bound, a y starting bound. It's going to be this one. This is going to be my starting disk, the one with the lowest y. And the y of that disk will be 0. This final disk right here, basically at this point. So what is the y coordinate of this point? Well, this point is where my x is equal to 2 line and my y is equal to 2x line intersect. So I can just plug in x is equal to 2 in there to figure out what that y is. And I will get 4. So this point is x, 4. And my y upper bound will be 4. So there we go. This is the hard part. Building the integral is the hard part. So now that we've completed construction of the integral, let's just crunch the math. So I'm just going to bang out this definite integral here. And if you do that math, you'll end up with 16 pi over 3. And that is it for this one. Alright, let's graph our curves. Starting with this one. It's going to look like this. Alright, a couple of lines here. X is equal to 4. Alright, y is equal to negative 2. All the points that have y's of negative 2. And x is equal to 0. Going to be these guys. Alright, the region of interest here is going to be this guy. And what line do we want to rotate it about? About the y is equal to negative 2. So this line. And we can imagine this 3D shape that rotating that area about will form. It'll form some weirdness. Something like that. Alright. So let's envision those disks. Alright, I see the disks, and here's my y is equal to negative 2 line. I'm rotating that area about. So let's get to finding those radii. So I locate them on my shape. And here is where they would be on my main graph. Alright, so it looks to me that these lines are y lines. They're not going to be the y coordinates of my green curve, because the y coordinates of my green curve are just these blue lines. But I know that at least I should keep my y is equal to rad x equation in this form. I should keep it in terms of x such that it gives me y's, because I'm going to have to bring that math together to create those y red lines that form those radii. So I'll start with radical x. And I know that when I plug in an x into this equation, it gives me a y. Plug in an x gives me a y. Plug in an x gives me a y. But I need a little bit more. I need those red lines. Well, it looks like I need to extend those y coordinates. I need to add stuff to it to get my red lines. Well, how about I add 2? If I add 2 to each one of these y coordinates, it'll completely form those red lines. Here's the y coordinate in blue, and I can add this orange of 2 onto it to make that red line. So I can add 2 to each one of these y coordinates popping out of this equation right here to form my radii. And you'll see some other teachers saying, all right, radical x minus a minus 2. But it'll give you the same thing. So it looks like my approach here is giving me the correct radius everywhere I can think about it. I mean, yeah, you always want to test your equation throughout your entire little area here just to make sure it's always going to work. You never know. But we know that it's working now. Nothing crazy is happening. So this gives me the radii of my disks. So of course I just want to square each radius times it by pi. That will give me the area of each one of these disks. And I want to take each one of those areas and multiply it by a little bit of height, and that height will be a little bit of x length. And of course, doing that will form the volume of that tiny disk. So I'll just multiply each one of my a's in my equation by dx. And of course, I want to add up all of these volume disks. And now this is an x integral. So what is my lower x? What's my starting x? Well, this disk right here will be the one at my lower x. It looks like it's at an x coordinate of 0, so my starting x is 0. And I'll add up all these disks here until I get to the final disk, which is going to be this one right here. And the x coordinate of that disk looks like it's going to be 4. So that will be my upper bound. And there we go. Integral is complete. Just got to crunch the math. And if I crunch that integral, I'll get 136 over 3 times pi. Alright, we'll do one more. Okie smokes. Let us graph our curves here. We'll start with this one. Now this is one of those annoying functions that's given in terms of y. Because of that, it's hard to graph. We're all used to thinking of y is equal to, 2x squared minus y squared and stuff like that. So maybe I can put this equation in terms of x by getting y by itself equal to something in terms of x. But if you look at it, it's not that simple. To get y by itself, I would have to basically complete the square on this right-hand side of the equation, which is annoying, so I'll just try to think in terms of y. So to help me graph this curve, I can rotate my main graph 90 degrees just to look at it like this. So I'm kind of treating x as more the dependent variable and y as the independent variable. And doing this allows me to just see this and say, okay, yeah, that's just going to be one of those downwards parabolas based on that minus 1 y squared. It just helps us to graph it easier. So it's going to look like something like this. And to get the exact graph, we want to think about those points of interest. X-intercepts, y-intercepts, local maxes and mins. So I'll think about y-intercepts first. That's basically where x is equal to 0. So I look at this equation and I'm like, okay, what y's will make this whole equation equal to 0? What y's will make x equal to 0? And that answer becomes more apparent if I factor out a y. So I know that if I make y equal to 0, x will become a 0. So I have y0, x0 as one of my y-intercepts. And I also know that if I make y2, this whole equation, x, will become 0. So here's another one of my points here. And since it's a concave down parabola, I know it's going to do something like this. And I'm not going to worry about this local max at the moment. Maybe I will later, but not right now. So I can bring this work over to our main graph. We have this point right here, And we also have my y to x0 point. That's going to be right here. So here is the curve. Alright, I also have x is equal to 0. All the points with x coordinates of 0, which makes my enclosed region this right here. And we are rotating this area about the y-axis. So just the same x is equal to 0 line right here. If I do that, I get another one of those football shapes. Here's my y-axis of rotation. Alright, so we got to envision those discs. Alright, so now for the disc approach. Here are the radii of each one of my discs. And on my main graph, here are those radii. These radii look like x's. X coordinates, x lengths. So let me take a look at this equation and just make sure and see if that's what we need. So 2y minus y squared. This equation gives me the x coordinates of these points. So I plug in a y to that equation and gives me the x coordinate of a point on this orange curve. And it looks like those x coordinates are exactly what I need. So, didn't have to do any crazy modifications there. Plug in a y and out comes the x, which is the r of the disk at that y. So of course I can just square each one of these r's, times it by pi. That gives me the area of the disk at that y. And to make it a volume, I multiply it by a little bit of perpendicular height, which will be a little bit of y distance, to make my dv the tiny bit of volume that that disk represents. So going back to my equation, it gives me the area of the disk at the moment. Got to multiply it by dy. So now this whole equation gives me the disk volume, the volume of the disk at that y, and of course I want to simply add up all these disk volumes. So what's my y lower bound? Well, this will be the lower bound for my y, this disk right here. And the y coordinate there is going to be 0. And I'll keep adding those disks up until I get to this last disk right here. Now what's the y coordinate of this point? Well, going back to our graphing work over here, we knew that that point was an x of 0 and a y of 2. So y, the upper bound, will be 2. And there we go. The hard part is done. We've built that integral. Now we just have to crunch the math. And here is the math worked out for this integral. And the integrals necessary to calculate these volumes, they are tedious, but notice that they're not too bad. They always turn out to be just inverse power rule antiderivatives. So just take it slow, write neatly, and stay organized, and you should be fine. You'll end up with 16 pi over 15 as your answer. So hopefully this disk approach, this disk method for calculating 3D volumes is making sense. The next volume calculation technique we're going to look at is the washers method, and it relies heavily on disk method. So just make sure you're really sharp with seeing these disks, calculating, forming the radii, the math that gives you the radii, visualizing those areas and all that stuff. Just really make sure you're getting the step-by-step process, because the next technique, the washer technique, really depends on understanding this disk technique.